Yeah, hi. Thanks for coming to my talk. My name's Noah Fleming. I'm from UCSD, and this is joint work with Tony Pitassi and Robert Robere. So I'm going to be talking about extremely deep proofs, and I promise by the end of this talk, you will have seen some very deep proofs. Okay, so this talk is going to be about trade-offs, which are a pretty ubiquitous phenomenon in complexity theory. So very recently, several works have exhibited kind of a new type of trade-off, a particularly strong type of trade-off. And these are known as supercritical trade-offs. So these are trade-offs where when one parameter is restricted, say, you can think of restricting the size of a circuit, then the other is pushed beyond worst case. So think of restricting the size and then pushing this, causing depth perhaps to be pushed way beyond worst case. So all examples of this phenomenon have been observed in proof complexity, to my knowledge. So the first instance was by Beam, Becken, and Pagliazzo, who showed a supercritical trade-off for resolution between proof size and another notion, which is proof space. A second and particularly relevant work was by Razborov, who showed a particularly strong trade-off for tree-like resolution. He showed if you take tree-like resolution and you restrict the width that it's allowed to use, then there's a CNF formula which requires doubly exponential size. And following this, there's been several other works that proved trade-offs between size and space, and also width and space for various proof systems. Okay, so in this work, we exhibit the first supercritical trade-off between size and the very natural proof parameter depth. Okay, so I'll motivate depth in a second. And we prove such a trade-off for resolution, KDNF resolution, as well as cutting planes. Okay, and for today, I'm just going to focus on the resolution proof system because it's the simplest, and our trade-offs for these other proof systems follow from the trade-off for resolution. Okay, so what's resolution? So it's a method for proving that a given CNF formula is unsatisfiable. So you're given a CNF formula and you interpret it as a set of clauses. So I've written an example down at the bottom, and you're allowed to derive new clauses from old ones using the following rule. Basically, it's called the resolution rule, and basically what you do is you take two clauses containing complementary literal, and you take their disjunction. That is, it's called resolving these two clauses. So you take their disjunction and remove the complementary literal. So throughout this talk, I'm going to denote by pi just a proof. So we can take these two clauses and resolve them to get x3. And our goal at the end of the day is to derive the empty clause. So the empty clause is falsified by every truth assignment. And because resolution is sound, that means we can only make like true inferences. That if we derive the empty clause, this means that there couldn't have been any truth assignment which satisfied the initial formula. So we can keep going. We can take these two clauses and derive not x3, and then using the resolution rule on them, we can derive the empty clause. Okay, so this is a simple resolution proof. And the complexity parameters of resolution that we're going to care about are, first of all, size, just the total number of clauses in our proof, or the number of lines. In this case, it's 7. Width, which is the maximum number of variables in any clause. So you can see some of the initial clauses have 2 variables, they're width 2. And then finally, depth, which is the parameter we're going to be most interested in, which is the longest root to leaf path in the proof. So in this case, it's 3. Just viewing the proof as a tree or as a DAG. Okay, and I'm also going to use this notation. So size sub res of F for a CNF formula F is the minimum resolution proof, the minimum size resolution proof of F. And similarly for width and depth. Okay. So depth, I claim, is an extremely natural parameter of proofs. So it's kind of analogous to circuit depth. So if you think about circuit depth, it essentially captures a notion of parallelism of a circuit. And you can think of the same thing for proofs. So resolution proofs capture the complexity of modern algorithms for SAT. So if we prove lower bounds on the size of resolution proofs, then this implies lower bounds on the runtime of these algorithms. And lower bounds on the depth imply bounds on parallelizability. Now, it's important to note that every CNF formula has a resolution proof of depth n, so like linear depth. However, this size may blow up to be 2 to the n. Also, many strong proof systems can be balanced, where balanced means that you can take a proof with size s and turn it into another proof with both size, maybe poly s, and depth, which is logarithmic in the size. However, so this can be done for like Frege or AC0 Frege, strong proof systems like that. However, for weak proof systems, they generally can't be balanced. In particular, for resolution, KDNF resolution, and cutting planes, these all can't be balanced. Okay, and we show an extreme case of this in this work. So this is our main theorem. So if we let P be any of these proof systems, resolution, KDNF resolution, or cutting planes, then there's a CNF formula on n variables such that there's a polynomial in n size proof of the formula. However, any sub-exponential size proof must have depth, which is polynomial for some polynomial that's greater than n, so supercritical. And our trade-off is smooth, so we can actually ramp this up. We can show that there's a CNF formula on n variables, which has a weakly exponential size proof, so like 2 to the n to the epsilon, or delta in this case. However, any sub-exponential size proof must have weakly exponential depth. So what this means is that we have this proof of 2 to the n to the delta size, but its depth is basically equal to its size. Like it's just a really, really long, skinny path. It's kind of a really paradoxical proof. So our general theorem is the following. So we're going to let epsilon just be some arbitrary non-negative real value. And C is going to be another real value parameter, which will control our trade-off. Okay, so then there's a CNF formula on n variables such that there's a resolution proof of size n to the c, 2 to the order c. However, any resolution proof of size roughly sub-exponential must satisfy the following relation, that the depth of the proof times the log of its size has to be about n to the c. Okay, and so instantiating the value of c here will give us the previous two trade-offs that I showed you, and smooth results in between. There's one caveat to our result, is that while the result is supercritical in terms of the number of variables, the formula itself may have n to the order c many clauses, and so not be supercritical in terms of the number of clauses. So supercritical in terms of the number of variables, not the clauses. And we'll come back to this later because this poses a problem in some open work. Okay. Yeah, so what is our proof technique? It's called hardness condensation, and this technique was introduced by Rasberov. So the whole idea is to find a CNF formula on capital N many variables, such that that formula has small size proofs, but requires large depth. So for resolution, we can just take the pebbling formulas. These have linear size proofs, but require depth, which is like n over log n. And then what we want to do is we want to compress the number of variables of the formula to some little n, which is much less than capital N, while maintaining that both A and B hold, at least for small size proofs. And the whole upshot of this is that the new compressed formula still is going to require approximately capital N over log n many variables, capital N over log n depth, but has only little n many variables. So if little n is sufficiently small, then we get supercritical trade-offs. Okay, so how do we do this compression? Well, the answer is lifting. So what is lifting? You've probably all seen it. It's basically one of the most powerful tools we have for proving lower bounds, and it's just composition. So I'm going to describe it in the setting of proof complexity. So we begin with a CNF formula on variables Z1 to Z capital N. And we're going to let G be some function on T input bits, which we're going to call our gadget. And now we can obtain a new function or a new CNF formula, which we call the composed function, or the composed formula, by replacing each variable Zi with this gadget G on a fresh set of T variables. So you should think of Xi as being a vector of T new variables. Okay. So these vectors of new variables, X1 to Xn, are typically disjoint. And this is a little bit of foreshadowing. And then, so what a lifting theorem does is if we let P and Q be proof systems, then a lifting theorem relates the complexity of P proofs of F to Q proofs of the composed function, F composed with G. Okay, so a very simple example is if G is the 2-bit XOR function. So in this case, F composed with XOR 2, we now replace each variable with a parity of 2 new variables. So for example, replace Z1 by X1 parity with Y1. And we can prove the following pretty simple width to size lifting theorem. So which just says if we start with a CNF formula F, that any proof pi of the composed function, F composed with XOR 2, must have size, which is lower bounded by exponential in the width of the uncomposed function. Or said differently, what we're doing is we're lifting lower bounds on the width of the uncomposed function to lower bounds on the size of the composed function. And also, we can maintain that the depth of this proof has to be at least the depth of proving the uncomposed function. So this is a pretty simple width to size lifting theorem. It can be proved by a pretty standard random restriction argument. Okay, so in this case, P is the resolution proof system, and so is Q. But we're lifting one parameter to a different parameter. Okay, and one thing I should mention is that this width to size lifting theorem is almost tight. So if F has proofs of size S and width W, then the composed function has proofs of size S times 2 to the W. So up to this S factor, this lifting theorem is tight. And you can show this just by basically simulating the proof of the uncomposed function to prove the composed function, where at every step, you just kind of locally simulate each XOR. And so the upshot is that the naive simulation is essentially the best, just simulating the proof of F, but at every step, just dealing with the XOR. And this naive simulation being the best is kind of a general theme of lifting theorems. And we'll come back to this. Okay, so typically in lifting theorems, P is a weak proof system, Q is a strong proof system, and a lifting theorem shows that the most efficient Q proofs of the composed function are just to simulate the most efficient P proofs of the uncomposed function with a little bit of overhead to handle the gadget. But our lifting theorem does the opposite. So it lifts depth lower bounds on a strong proof system to depth lower bounds on a weaker proof system, albeit the new depth lower bounds we get are much stronger. So here P is resolution and Q is size bounded resolution. So resolution where we're not allowed to exceed some size bound on the size. Okay, and our proof idea is the following. We want to find a gadget G such that the number of variables, little n, of the composed function is much smaller than the number of variables of the uncomposed function, capital N. And then we want to show that any small size resolution proof of the composed function will require basically the same depth as just proving the uncomposed function. Okay. So in order to do this, we need to define what our gadget is. So our gadget is just going to be the XOR function, but with a bit of a twist. The twist is that these variables that each XOR depends on, so you should think of xi as being a vector of variables. So the sets of variables x1 to x capital N will no longer be disjoint. This is unlike the width to size lifting theorem I showed you a minute ago. And the fact that they're no longer disjoint will allow us to compress the total number of variables. Yeah, so composing will reduce the total number of variables to little n, which is going to be much smaller than capital N. So to define our XOR gadget, or the way we allow these XOR gadgets to share variables, we're going to use a simple like bipartite dependency graph to represent this. So capital N, is the number of initial variables. So we're going to have capital N left vertices. And here capital N, we're actually going to set to be n to the c, like little n to the c. And the number of right variables is, or right vertices is little n. And now there's an edge between one of the initial variables, the original variables, to a new variable if the original variable is replaced after composing by an XOR involving that new variable. Okay, yeah, so this is basically just saying what I just said. So we're going to let F compose with XOR sub G. So G is defining the dependency graph here. Is going to replace each variable Zi with the parity of all of the variables that are adjacent to it. So here's an example. So you can see that Z1 gets replaced with X1 parity with X3, Z2 with X1 parity with X2, and so on and so forth. So in this way, we can define these XOR gadgets that share variables. So a simple example, let's say that Z1 or not Z2 and Z5 is a CNF formula. We compose it with this XOR gadget. Then what we're going to get is this. So we replace Z1 with its XOR. So X1 parity with X3, and so on and so forth. Okay. And then, so one issue with doing this composition is that since we're shrinking the number of variables, doing this composition can introduce some dependency between variables. For example, you can see that Z1 depends on X1 and Z2 depends on X1. So if we learn the value of Z1, if resolution learns its value, then it also learns some information about Z2. And that can be bad because it can lead to like some really annoying like correlations. So we want to avoid this. And the way we're going to avoid this is we're going to require that G is sufficiently spread out. So if G is sufficiently spread out, then learning the value of one XOR won't reveal much information about any other. And this allows us to show that the best resolution proof of the composed function should essentially be to simulate the best proof of the uncomposed formula. And by spread out, we're just going to mean that G is sufficiently expanding. Okay. And then so our final gadget is going to be XOR sub G for some expanding G. And so the main workhorse of our trade-off is going to be the following depth condensation theorem by Razborov. So he stated this for tree-like resolution, but it's not difficult to see how to extend it to resolution. So the depth condensation theorem says that if you take some expanding graph G, some unsatisfiable formula F, then if pi is a resolution proof of the composed function with sufficiently bounded width, this R is, it depends, R is going to be a parameter in the expansion, but just think of the width as being somewhat bounded. Then the depth times the width is at least the depth of the uncomposed function. Okay, and so one of the big contributions of our paper is we give a significantly simplified proof of this theorem. Okay, and so if you take a moment and you plug in for F, the pebbling formula, then we and we let G be a bipartite graph with capital N left variables, little n right variables, where capital N is n to the c, then this becomes that the depth of the proof times the width of the proof is at least n to the c over c log n, which is basically what our trade-off should be, except for we have width here instead of size. Okay, so in order to remedy this, we combine this with the width to size resolution, width to size lifting theorem for resolution in order to prove our main trade-off. So here's the width to size resolution, width to size lifting theorem for resolution. Yeah, and so combining this with the depth condensation theorem proves the following main result, which is exactly what I showed you before. And now the trade-offs for the other proof systems can be obtained by an additional step of lifting. So for cutting planes, we use the lifting theorem of Goose, Garg, Kamath, and Sokolov. And for KDNF resolution, we prove a resolution width to KDNF resolution size lifting theorem, where the gadget is 2-bit XOR, by using the switching lemma of Sekerlin, Busson, and Pagliazzo. Okay, so in the last bit of this talk, I want to talk about supercritical trade-offs for other models of computation, in particular size depth trade-offs. So I think this is a very natural question. We make some preliminary progress on this question, but I think there's a lot of great open problems here. Okay. So a very natural model of computation to look at is monotone circuits, because we know these are very tightly connected to proof systems. Furthermore, there are functions for which poly-size monotone circuits require a near maximal n over polylog n depth. So a natural question is, can this be extended to a supercritical trade-off? If you restrict the size, can you show that the depth has to be above n? Okay. And one thing you might be wondering is whether such a supercritical trade-off just follows immediately from our supercritical size depth trade-off for cutting planes using the method of feasible interpolation. So feasible interpolation basically connects cutting planes proofs to monotone circuits. It shows that for any cutting planes proof of unsatisfiable CNF formula implies a monotone circuit computing some associated function with the same topology, that is the same size and the same depth. Okay, so this is where our caveat at the very start is going to come back and bite us. So the number of variables of this formula is actually equal to the number of clauses of the unsat CNF formula that we began with. And if you remember, our supercritical size depth trade-off is only supercritical in terms of the number of variables, not in terms of the number of clauses. So the number of clauses is n to the order c. So what we obtain is from this is very strong depth lower bounds but they're not supercritical. Yeah. So our trade-off does not immediately imply supercritical trade-offs for monotone circuits. However, a natural approach to getting these supercritical trade-offs for monotone circuits would be to improve our supercritical size depth trade-off for resolution to work to be supercritical, not only in terms of the number of variables, but to be supercritical in terms of the number of clauses. So in particular, using the current lifting theorem from resolution to cutting planes of GGKS, in order to obtain a supercritical size depth trade-off for monotone circuits using interpolation, we would require that the following conjecture is true, which states that there's a CNF formula on M clauses such that any, say, quasi-polynomial size resolution proof requires depth, which is at least M times n to the 4. This quantity just comes from the lifting theorems. So we show that if this conjecture holds, then this implies supercritical size depth trade-offs for monotone circuits. We also state the following approach for resolving this conjecture, which is to study whether the Bensasson-Wigderson size-width relation can be balanced. In particular, we'd like to prove or disprove the following: that any KCNF formula on M clauses, that if there's a size S resolution proof, then this implies that there's a depth, which is at most linear in the number of clauses, and it satisfies the size width relation. So the width is approximately square root n log S. Okay, and the reason why we think this is a really good problem to work on is that there's a great win-win situation here. In particular, a positive resolution would give a counterexample to this conjecture and a surprising upper bound on depth for resolution. Whereas a negative resolution would give a conditional, potentially conditional, size depth trade-off for monotone circuits. Conditional here just means conditional on like a significantly powerful lifting theorem from resolution to cutting planes. So it depends on the degree, like the parameters of your negative resolution. And the final question I want to end with is just whether you can prove supercritical size depth trade-offs for non-monotone circuits. Of course, under some like assumption, like cryptographic assumption or something like that. All right. Yeah, thanks for sticking with me.